Okay, sample problem 8.12. Draw the Lewis structures of A boron triiodide, Bi3, arsenic pentafluoride, AsF5, and xenon tetrafluoride, XeF4. Okay, so unlike the previous sample problem where it was an odd number of electrons, we actually do have even number of electrons here, but there are certain structures that are non-octet for the central atom. And that's the key to this. We generally observe this phenomenon for the central atom, not the surrounding atoms. So the surrounding atoms should have 8, unless, of course, it's hydrogen, which would have 2. Certain elements sometimes exhibit fewer than 8. So these are often referred to as electron deficient. And the most common of these elements are beryllium, boron, and aluminum. And we're going to focus on these two here. These ones often will exhibit the case where they have 6 valence electrons in their Lewis structure. So boron, aluminum, possibly you'll get 6. Then we have elements that have more than 8. And so those generally start with the third row. Okay, so those would be phosphorus, sulfur, chlorine, if they're the central atom. Below that, arsenic, selenium, and bromine, tellurium, iodine, and actually even a couple of the noble gases, such as xenon. Radon maybe, but radon is radioactive. It's hard to study. Okay? So these often have what we call expanded octet. Greater than 8 electrons. Could be 10 or 12 or even 14 electrons. Okay? So if you take a look at the examples here, boron, there's an example of the electron deficient. Arsenic, there's an example of the expanded octet. Xenon, another example. It's the central atom that we're concerned with. Okay? Now, let's go through each one. Let's do boron triiodide. Remember, when we draw Lewis structures, we assume a single bond to the central atom to each of the surrounding atoms. Let's count up valence electrons. Boron is in group 3A. So it has 3 electrons. Iodine is in group 7A, so it has 7 electrons. There are 3 iodines, so 21 plus 3 gives you 24. We've already used 6, that gives us 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And what I'm going to claim is that for boron or aluminum, if there are only 3 atoms surrounding it, the best Lewis structure is the one in which you just have a single bond to each surrounding electron, and so you only have 6 valence electrons. Okay? We can use formal charge to justify that. If you do a formal charge calculation for the central atom, in this case boron, remember it's the number of valence electrons, which is 3, minus the number of associated electrons, which is lone pairs, which is 0, plus the number of bonds, which is 3. 3 minus 3 is 0. Remember we said better formal charges are ones where you get 0? We can use that argument to justify the electron deficient structure in boron triiodide. The next one is arsenic pentafluoride. Now, I'm going to point out that for arsenic pentafluoride, you can't have an octet on the arsenic very easily because there's 5 surrounding atoms, and there's got to be at least 1 bond to each atom. So that's 10 right there, and that's actually what happens. For arsenic pentafluoride, now this is the first structure we've seen so far where we've got more than 4 surrounding atoms, so I'm just going to draw it like a little pentagon. There's 5, like a star. There's 5. Count up the number of valence electrons. Arsenic is in group 5A, so that's 5. Fluorine is in group 7A, so that's 7, but there's 5 of them, so that's 35. So that gives you 40, but we've already used 10. So we've got 30. So 1, 2, 3, 4, 5, 6. Remember we say you get the surrounding atoms up to 8. So by adding 3 lone pairs to each of those, we get up to 8. This method of Lewis structure works very well. So now we've used 30. We're out of electrons. The arsenic has 10. That's an expanded octet. But I said earlier that there are certain elements where that can happen. Phosphorus, sulfur, chlorine, if they're the central atom, that can happen, expanded octet. Again, we can justify this by considering formal charge of the arsenic. It's in group 5A, so that's 5 valence electrons. The number of associated electrons is 0 plus 5. There's a 0 formal charge. So it appears as though the arsenic is forming a bond to 5 different fluorines to reduce its formal charge to something around 0. Okay? The last one is Xenon Tetrafluoride. Okay? So Xenon Tetrafluoride. The only issue here is for Xenon Tetrafluoride, how many valence electrons do we use for xenon? Well, it's in group 8A, so that's 8 valence electrons. Fluorine is in group 7A, so that's 7. But there's 4 of them, so that's 28. 28 plus 8 is what, 36? But we've already used 8, so that gives us 28. So we've got 28 to go. So again, put 6 around each surrounding atom, unless you run out, but we're not going to run out because we've got 28 to work with. So there's 24. So we got 4 left. Where do we put them? We put them on the xenon. Not much room to put them in there, so I'm going to put them on the side like that. Okay. So now, how many electrons does the xenon have? This central atom has 8, 10, 12. It's got 12, right? 4 bonds is 8, plus 2 lone pairs is another 4. That's 12. How could that be? How could xenon have 12? Again, let's do a formal charge. Xenon has 8 valence electrons. It has 2 lone pairs, so that's 4. And it has 4 bonds. That's 0. So it appears as though there's something to this formal charge logic. Okay? Now, I will point out there are disagreements in the chemical sciences over what's really going on here. Is there such a thing as an expanded octet? I will not claim that this is, I don't want to be dogmatic about it. People disagree over this issue. But your textbook analyzes it this way. Most chemistry textbooks will analyze it this way. There are certain elements that they appear at least, we'll say they at least appear to have more than 8 electrons in their Lewis structure. Expanded octet.